Now it is. Okay. Here I've written down the Feynman rules in slightly different normalizations that I did yesterday. As I said, there are some conventions in writing down Feynman rules. The main thing I want to remind you of is that indeed we have these two propagators for electrons and for the photon, and there's this single vertex. And then from these Feynman diagrams, well, they are constructed from these propagators and the vertices by connecting them in arbitrary ways. Yesterday I described the Feynman diagram, really the simplest one, but in general the rules tell you that if you have a certain number of external lines in your Feynman diagram, you have to connect all of those external lines using any possible way using the propagators and vertices. And this in particular will allow the possibility of having loops in your diagrams, and this corresponds to internal parts of your diagram where particles actually run around in loops without being connected to the external lines. And this gives rise to corrections to the diagrams, in particular the ones which I described yesterday. And so this lecture I will describe one of those loop corrections, and in particular the one that's going to determine the way that the coupling constants in QED depend on energy. So there are three kinds of important loop corrections in QED, and here I've indicated what the diagrams are that correspond to them. There's first of all a possibility that a photon propagator gets corrections due to the fact that there are loops, fermion loops, that arise when the photon actually for a certain amount of time splits into a positron electron pair, and then this is a virtual pair which exists for a certain time, and then it reconnects and annihilates again this electron positron pair and gives you again the photon. These virtual processes have to be taken into account in doing the Feynman diagram calculations. So this will actually provide a correction to the propagator of the photon because, well, as you see, this is sort of the same external lines as we have for the propagators, and it's this diagram which will affect eventually the strength of the electromagnetic force and determine the way that the coupling constant will depend on the energy scale. There are other diagrams which have to do with corrections to the mass of the electron. Here we have the electron propagator, and then there can be a virtual process where the electron emits a photon which reconnects again and is reabsorbed at a later time. And then there's a loop in here, and in all of these diagrams, because there's a closed loop, the momentum which goes through here, so here the momentum would be k, and we have a closed loop around here where the momentum is determined only by momentum conservation, and similarly here, but then we have to integrate according to the Feynman rules over the momentum that goes around in the loop. And this will, in particular in these loop corrections, give rise to integrations over certain expressions, and as we will see, those expressions can, these integral expressions can be ill-defined in general if, well, the integral itself is not convergent. And so we will have to learn to deal with this in quantum field theory in a way that we can make sense out of those loop corrections by making those integrals convergent in certain ways. So evaluating loop amplitudes involves regularization procedures where you make the loop integrations finite, and then eventually you have to get a result that you can compare to experiment. And this is called the process of renormalization, and I'll describe this in detail later on. Finally, there's a third correction which involves a vertex correction. So this was the vertex which we had in the Feynman rules. And then there can be corrections to the vertex due to photons that are being exchanged between the two electrons that connect at the vertex. And this will have an influence on the way that electrons actually interact with photons. So this gives corrections to the photon-electron interaction. So what I will do actually today is discuss mainly this diagram and the way it will affect the amplitude that I calculated yesterday. So I'll go back to that and include now this correction to that diagram. I will return to the blackboard, so I'll switch this off. So yesterday I described an amplitude for electron-positron annihilation that then produced a muon pair. And so we had a diagram of the form, a simple diagram like that. Where these were the electron lines and these the muon lines. And as you see in here we have a propagator of a photon. And so what I will do later on is include in here the correction to the photon propagator due to loops entering in this internal propagator. The expression which I had actually, well, I'll write it down in a slightly different notation which is a little more precise. I introduced this quantity dW, which I called the transition probability. It includes actually also integrations of the initial momenta. So if I have momentum P1 and P2 for the incoming two particles, then here this W must be some expression which I will call just simply W times the integral measure of these momenta. These are the same integration measures which I have been writing down all along. These are integration measures which are Lorentz invariant. And since I don't want to write them down all the time, I define now this quantity W, which I want to, which I gave an expression for yesterday. And this expression was, if you do the Feynman diagram calculation, you'll find 2e to the fourth, and then a combination of Mandelstam variables which was S, which was P1 plus P2 squared, and if I have here K1, K2, and I'll actually leave out the arrow, so I'll think of those as being four momenta. So I include in here the four momentum P1 plus P2 squared. And so this is a Lorentz invariant expression. And similarly we have T, which is P1 minus K1 squared, and U being P1 minus K2 squared. So this is the expression for W for the process E plus E minus gives you mu plus mu minus. There's actually an interesting fact that if I look at this diagram, I thought about time going this direction. So indeed I have two particles that annihilate and produce the photon, and then the photon decays again into a muon pair. But the same diagram appears if I look at another process where I take two particles that collide, they just scatter elastically by exchange of a photon. So the same Feynman diagram calculation can be used to also calculate a scattering amplitude where I have, say, an E minus and a mu plus, which simply go to E minus and mu plus. So it's elastic scattering between two charged particles. I'll have a similar expression. The only thing is then that the role of what I call so this must be the incoming momenta and the outgoing momenta is interchanged, because in this process what happens is I let time go in this direction. So actually these are the two incoming momenta and these would be the two outgoing momenta, and so the role of what is called S, T and U will be interchanged, and so the expression for this process is very similar, except what happens is actually this expression s and t get interchanged. So you get s squared plus u squared divided by t squared. But it's a similar result, and actually in this interpretation it's even more clear that what we're doing is actually having two charged particles which scatter off each other, and so what we're actually measuring here is just the interaction between two charged particles, and this interaction determines the strength of the electric force, and so it's in this way that the value for E can be determined by experiment. So the value for this coupling constant, the electric charge, can be read off from this expression. Actually, it's very more useful and also more convenient, or let's say conventional, to introduce this parameter alpha, which is E squared divided by 4 pi, which is usually called the fine structure constant, and has this famous value 1 over 137. So approximately, and this is actually true at low energies, alpha is 1 over 137. But what we'll find actually is that if we go to higher energies, this value is no longer true, and that this coupling alpha will start to depend on the value of the energy that we do the experiment. So the corrections which I want to include now are indeed these loop corrections that affect these diagrams. So there must be a correction, a loop correction, which looks like this, where we have these internal incoming lines. Then we have the photon propagator with an internal loop, and the outgoing lines. And the momenta P1, P2, I introduced a momentum variable Q, which is actually the sum of P1 and P2. And now you can look at the momentum conservation in this diagram. Q will be the same momentum that comes out here. And then there's this K2 and K1. I'm out of symbols. Anyhow, I'll actually introduce a momentum K, which is not, of course, not the same momentum as the external momenta K1 and K2. So it's an additional momentum variable, which is going to be the momentum that I have here in the loop. So this line here will carry a momentum K, and then just momentum conservation tells you that this line should carry a momentum K plus 2, Q plus K. And so this part of the diagram involves an undetermined momentum K, which is not determined by the external momenta, and that's the momentum I have to integrate over in this expression. Well, the Feynman diagrams you can write down in a similar way, and actually you also have to include the external wave functions again and do these sums, but as you can see from the diagram, the only part that really changed is this part in here that involves the propagator of the photon. And indeed, the whole effect of this diagram can be taken into account by replacing the Feynman propagator for the photon, delta mu of Q, which I used as a symbol for my propagator. Actually, what I'll write down actually is a modification of the inverse propagator. So the inverse propagator, instead of having 1 over Q squared, will have a Q squared on top. So it's I Q squared A dem nu. That's going to be changed to get a correction. There will be the same Q squared and A dem nu. But then due to the correction of this diagram, I get an additional function or expression which I call pi mu of Q squared, which is correcting the propagator. This diagram, by the way, is called the vacuum polarization diagram. And there's an intuitive reason why we call it like that, is because what it describes is that if you have two charged particles, then there's these virtual clouds of particles, which I have here, which are responsible for these loops. What it actually tells you, if you have two particles close together, that there can be a spontaneous creation of a pair of electron and a positron, which for a short time exists, and where the electron and the positron move towards each other a little bit, so that the charge of the original electron is screened a little bit by these vacuum fluctuations. And this is actually also the intuitive reason why we know that the way that these electrons and muons attract each other is affected by the vacuum fluctuations. There's a certain polarization of the vacuum because of these vacuum fluctuations, which screens the charge of the electron. And the amount of screening is dependent on the energy scale that we look at it. So that's why this is called the vacuum polarization. And this intuitive argument will actually make clear that at higher energies, we have more energy available actually to create these virtual pairs, that the screening is better. So indeed the screening, the charges get more and more screened at higher energies, so that the strength of the electromagnetic interactions will be going down. Actually well, actually it's the other way around. Anyhow, so the intuition actually about whether it becomes stronger or weaker is something that cannot be applied generally, because what we'll find is that depending on which force you're looking at, namely the strong force or the weak force or the electric force, the way that these fluctuations affect the strength of the coupling constant will be dependent on what force we have. So in certain cases the force becomes stronger, and in other cases the force becomes weaker at high energies. Actually in the strong force, that's where the force becomes weaker. This is called asymptotic freedom. Here you'll find that the strength will actually increase in going to higher energies. Anyhow, to determine which way it goes, you have to evaluate these diagrams, and the diagram calculation will tell you precisely the way that the coupling constant will be affected by these quantum fluctuations. So let me write down now the expression for this quantity pi mu nu using the Feynman rules. Q squared pi mu nu, which is also will be a function of Q squared, is going to be an expression. Well, it involves only this part of the diagram, so I will not write down, of course, again, these vertices. I'm going to write down only those vertices that are contained in this part of the diagram. So pi mu nu of Q corresponds to only that part of the diagram. So it has actually two indices, mu and nu, corresponding to the indices of the external photon lines. But I'll write down only the expression for the internal electron lines. So there are two vertices, so there's an E squared, some normalization factor. Then there will be an integration over this momentum k, and since it's a 4 momentum, I have to integrate over the 4 direct k values. And then the expression involves, again, a numerator and a denominator. In the numerator, I have a trace over the gamma matrices which enter in this loop. The vertices gave me gamma matrices, and also the propagators contain expressions with gamma matrices. So I'll get a trace over gamma matrices, gamma mu coming from the first vertex. Then there's the numerator of one of the propagators. Then I have the second vertex, so I have to go around the loop, and actually there's a rule to go around the loop in the other direction from the arrows, so that you get here the next vertex, which has a new index. And then I'll have there's another momentum, which is k plus q, which is inside the trace. And so there's quite a complicated expression which you have to evaluate using identities that tell you how to evaluate those traces over gamma matrices. And then in the denominator we have the parts coming from actually the propagators here, and they have the usual form k squared minus m squared, and I'll leave out the I epsilon just to make it a little simpler. The I epsilon actually is needed to tell us always how to do these integrations, because the way to evaluate these integrals is by doing the integral in the complex plane. And so there's a certain prescription that you have to use how to deal with these denominators, in particular the poles that arise in these denominators, which are at the values where this vanishes. There are certain poles, and you have to specify how to deal with those poles in the denominators. And so the I epsilon prescription is something that is needed to give you those, to get the right answers. I won't really evaluate this diagram, so I'm not going to write down a long calculation. I will actually give eventually a flavor of what kind of integrals you have to do, and also the kind of difficulties that you will meet in doing those integrals. Yes? That's right. So that's right. So what I've written down here is the contribution of just the electron pair going around, but there will be a sum of contributions of this type. So actually this vacuum polarization, all the particles, charged particles that we have, all contribute to these diagrams. So there will be a sum of expressions here where you indeed have to include here particles of arbitrary mass. Actually, which particles are important is also, of course, dependent on the energy that's being, going through this diagram, because actually you only have to include those particles whose masses are below the energy scale that we're looking at. And also at high energy scale, so if Q is very large, then basically you'll see that we can ignore the fact that we have a mass in here. And this is also the simplification which I will make here, is to look at the process where indeed we have a high momentum Q, so that the mass of the electron can be almost neglected. And then this will simplify my calculation. But indeed, if you go beyond, say, the muon mass, you have to include muons, and the taus will come in at higher energies even. And so the fact that massive particles only come in when the energy scales get higher is also important for us to ignore any particles that we don't know of. I mean, there may be particles that exist which are charged, which have very high mass, and we don't have to include them in here because we know that their contributions are suppressed by 1/powers of their masses. But you're right, this is just one contribution, but there will be a sum of contributions. And actually the way that the coupling constants depend on the energy scale is actually going to tell us a little bit about what kind of particles we have to include. And the fact that we can confirm the loop corrections by experiment is something that tells us that we have included all the right particles in our calculation. But the electron is the first important one because it's the one with the smallest mass. There's one fact that's important and will be helpful in simplifying the calculation, and that's what I mentioned yesterday, that the photon has a gauge invariance, and this means that actually these photon lines, there will be restriction on the coupling that a photon can have to a vertex. These vertices, which I have in the diagram, and also actually the same applies here, the interaction vertex comes from a term in the Lagrangian, A mu, J mu, where this was a current, which you remember we wrote as psi bar gamma mu psi. And the fact that there's a gauge invariance, namely an invariance under a mu going to a mu plus 1 over e d mu chi, must ensure us that there's no, well, to have gauge invariance, then if I make this shift in the gauge, in the photon field, the current must be conserved in order for this term to drop out, because then by partial integration, if I integrate this and use the fact then that d mu j mu is equal to 0, I'll find that the longitudinal component, which I call the component in here, must drop out. Well, I can transform this now to momentum space, and then it will tell me that if I take this external line and I, take actually this, what I have in here, includes precisely this current, because as you can see, the a mu, which is precisely the photon line in here, and the current, which has these two electron fields in them, is precisely responsible for these two electron lines. And this condition, d mu j mu equals 0, actually will tell me that if I take now the inner product, well, not with the derivative, but actually if I go to momentum space, you take the inner product with q being the momentum with pi mu. This must be equal to 0. This is called a Ward identity. It ensures that the longitudinal component of the photon, which is in the direction of the momentum, does not couple to this diagram, and this is what's the meaning of gauge invariance. And so imposing these conditions actually will tell you that this expression cannot be an arbitrary expression in terms of momenta and so on. It must satisfy these conditions. And this can be used then to show that pi mu is from the Ward identities. It follows that q squared times pi mu of q squared. I'll actually write down only the expression for pi mu q squared. Must be of the form some combination of eta mu and q mu q nu, which indeed satisfies precisely this condition. If you would contract this expression with k mu, then you'll find, using just the fact that, well, it's not so difficult to work out, that this indeed will vanish. But then there's some arbitrary function pi, so without any indices, which is still a function of q squared. And then, well, actually there's this expression which I had originally for pi mu of q squared. Evaluating this using the gamma trace identities, you indeed find it does have this form, and I won't go through the gamma matrix algebra. I'll just write down for you now an expression for pi of q squared, where I give the expression also in a limit, where I assume that q squared is large, so that indeed I can ignore the fact that I have an m squared in here. So I'm going to assume that q squared and also the loop momenta k are large, and so the m squared, which is in here, I will then be able to ignore. And so I'll end up with a simplified expression which still has the same integration over the form momentum k. And actually what I took from the numerator is precisely these parts of which is I've taken outside. So pi of q only will include the denominator, and so there's a 1 over k squared, which is due to this propagator, and then the q plus k squared in the other part. So this is what this function will look like. And this integral is the integral we have to do. And then if you just look at how these integrations behave when k becomes very large, there's a 1 over k to the fourth. If you take all powers of k here, if k is very large, it's something like 1 over k to the fourth. But the integration in the 4 momentum space also involves powers of k. If you think about the volume of a sphere in a 4-dimensional space, it goes like k to the third. But then integration of something like that goes like 1 over k over a single variable is a divergent integral. So this integration, just by looking at power counting, what's it called, by looking at the powers of k that enter in here, it will tell you that this result will be infinite if you would just simply integrate it naively. So what we have to do is actually, well, I already indicated in the beginning, the way to make sense out of these integrations is to use a procedure which is called regularization. So we have to regularize our loop integration. And the way to regularize, and I'll take the simplest way possible in here, and that's, for example, we can take this integral, which is actually an integral over Minkowski's signature space, but we're gonna can rewrite this integration through an analytic continuation to Euclidean variables. So we're gonna go to Euclidean space. And then I can talk about the length of the vector k, and I'm going to just assume that in Euclidean space k is going to be not larger than certain value lambda, which I call the cutoff. So I'm going to cut off the integration at a certain high momentum, which I call lambda. And of course, eventually I would like to take lambda to infinity, because I've now put in some cutoff scale, which I said, well, I don't want to integrate over that scale, but I'm going to just introduce it and then see what the result is, and then eventually I want to, of course, get an answer that should not depend on this scale, because it's an arbitrary scale that I've chosen, well, just at random, but the answer which I want to get is something I don't want to be dependent on this random choice. Now, if you do this, and I'll omit again a little bit of the details. This integration can be done then in the following way. I'm going to write this momentum integral in terms of the radius, the absolute value of k, and say some angular components. And then you'll find that this whole expression can be written as well, there's some normalization factors that come in, for example, from the volume of a sphere in 4 dimensions, because I have this 4-dimensional integral to do. So the 1 over pi to the fourth will become a 1 over pi squared, and there's some other numbers that come in. But then there is an integral which I'm going to do over the radius. Actually, I will take k squared to be my integration variable, and then in the expression, if you do the counting, it will go like 1 over k squared, and the integration region is from lambda squared, which is my cutoff, and I start at my value q squared, which was the variable which everything depends on. So it will enter in, actually it entered in here in this denominator, but I can also put it here in my integration region. And this integral you can do, it's a logarithm, but it has a logarithm with two boundaries, two values between the integration region. And so this expression will give you, well, the following result, that I'll just write it down here. So I already indicated that pi mu has this form, and then pi of q squared is, sorry, yes? Well, actually what I've done is taken this k squared together with a part of the volume which I have in here. So, where yes, that's actually I shifted my integral in such a way that the thing that I've left here is actually this object. So the lower value of this is actually q squared. Anyhow, the expression which I get is a logarithm of the cutoff divided by q squared. So it will be, well, actually, I can, if I change the sign, I'll get actually q squared over the cutoff squared. So that's the final answer. So this actually will be then combined together with the original term which I had in my first three-level diagram calculation, which I described yesterday, and I have to include this correction now to the propagator of my photon. So I take this expression, put it in here. This gives me pi mu nu, and this I insert in my inverse propagator, and it's that propagator that I have to use in my Feynman diagram calculation. Well, the way that the propagator affected the calculation was actually through giving eventually the 1 over s squared in my answer for my scattering transition probability. So what it will this whole calculation, what it will do is it will modify this expression, not here the expression in the numerator, it will modify actually my expression in the denominator. And it will modify it in the following way, that I already had my original answer, which I can write as, say, 1 over 1, and then there will be a correction coming from the inverse propagator. And the fact that I wrote down the inverse propagator tells you that this correction will come in the denominator of my answer. So in here I'll get 1 minus e squared over 12 pi squared times the logarithm of q squared, and q squared is nothing but s. So it will be s divided by lambda squared. And this expression actually is the correction to the amplitude, but what I've written here actually is the square of the amplitude. So this will actually be squared in my final answer. So this is the result if you include both the three-level and the one-loop expression for the amplitude. And as you see, it has modified, well, not this part, it has simply modified in a way the fact, the thing that multiplied this part of the expression. Yes? Yes, that's indeed formally what you have to do. So there seems to be intuitively a problem here. We have done a calculation, we've introduced an arbitrary scale lambda, and our final outcome is something that depends on lambda, and sending lambda to infinity gives you a nonsensical answer, namely this expression will again diverge. So this is where the next step comes in, and this is called renormalization. And the basic observation is the following. Here I've done a calculation. I've done a calculation using Feynman rules and Feynman diagrams, and in there I included my coupling constant, which I called E. Eventually I get an answer. It's nonsensical, but I know that physically, of course, I get finite answers when I do the experiment. And of course the value for E should be determined through experiment. We have to measure what E is, and we can do it by looking at one particular experiment and say, well, compare this result now to that experiment, and then we compute what E is from that experiment. So we have a physical value for E being the result from that experiment. Once I then determined E from one experiment, then I've determined this coupling constant, what its value is. But I know that this expression depends on lambda. So if I do this experiment and measure what E is, I will actually find an answer E, which can be a function of lambda. And this is actually the key step, is that we have still a choice here to choose what we call E in our expression. And we're going to choose E in such a way that we reproduce an experiment, say at a certain energy scale, and that is what we're going to call our physical value of the coupling. So these words I will make precise and write down the formulas that go with it. So the starting point of renormalization is actually to take actually the original calculation which I had, namely without the loop corrections, and then do my experiment at a certain value of energy. So I'm going to look at this experiment and I'm going to take S to be at a certain value, which I will call mu squared, which is an energy scale. You shouldn't confuse mu with the mu's for the muon. So this is going to be some energy scale, mu squared, at which I'm going to do my experiment. And I'm going to define now a physical coupling and I'm going to call it E of mu. In such a way that this expression is going to be 2e mu to the fourth times these variables I wrote down before. And this is going to be a measurement. So at a certain energy scale, I'm going to measure what E of mu is by taking this identity to be true. This E of mu is not the same E which I have here, and I'm going to make that clear by putting a 0 here, because I have the physical coupling constant here, but this is going to be called the bare coupling constant E, E0. So E0 is the bare coupling. And now what I'll do is actually take this expression which I calculated and then put it equal to my physical coupling over there. And you see that, of course, this part of the diagram is the same, so I only have to compare the other parts in here. So I get from this, well, actually I can see I have e to the fourth here and have this squared. So I'm going to compare that to e mu to the fourth in this expression. And that then we learn that actually e squared of mu, so I'll take actually the square root, must be equal to e0 squared times 1 minus e0 squared over 12 pi squared times the logarithm. And here, there we had in our expression s over lambda squared. S is equal to mu squared, so I'll write down here mu squared over lambda squared. And I left a little bit of space in here because this is my physical coupling, and I would like to determine E0, the bare coupling, so that this equation is satisfied. Now on the right-hand side, we have our cutoff, lambda. But I'm going to choose, of course, the solution in such a way that this is realized, but then I have to choose E0 to be dependent on lambda. So the left-hand side is independent of lambda. It's the right-hand side that depends on lambda in two ways. First of all, lambda appears here explicitly, but I'm going to choose E0 as a function of lambda. in such a way that this identity is satisfied. So this is the measurement I did at a certain energy scale. I did one experiment, say at S equals mu squared, put it equal to this expression. This gave me the physical coupling, and then I read off what E0 of lambda is. And this is what I'm going to now put in the rest of my calculation. So I'll take this to be my physical bare coupling, and then in here I get then the right answer if I take E0 now in this expression to be that function E0 of lambda. Is there a question? I hope it's clear what I just did. So just to repeat, in the Feynman diagram calculations, I used a bare coupling constant and a cutoff. And the bare coupling constant, I made a function of the cutoff in such a way that the final answer that I get reproduces the right answer, which I can compare to the measurement. And this is going to tell me also what the answer looks like at other energy values, because now I've taken that solution, that expression for E0 of lambda, put it in here, and now this tells me what the outcome should be at other values of the energy in here. However, it still seems to depend on lambda, but in a sort of complicated way, namely lambda appears here and lambda appears here. But I can actually simplify the expression by, or change the expression even, by using now this identity. So I know that this is satisfied. So what I will do actually is eliminate E0 of lambda in favor of E of mu. Let me write it down over there actually. So I see in here that I have now this expression, and it involves precisely this combination again, E0 squared lambda 1 minus E0 squared lambda. Sorry, there's a minus 1, I think, which sorry about that. There was an omission in my original comparison. I read off from this expression the powers of E0 squared in here, but I forget the fact that this actually entered in my denominator as a 1 over this factor. So this is actually the equation which I'm imposing. And in this expression over there, I still have the similar combination, E0 squared of lambda, and then there's E0 squared of lambda over 12 pi squared times the logarithm of S over lambda squared. So this is the thing that enters in my calculation, and this is what I had, sorry, again, minus, I'm putting too much brackets here. It's E0 lambda squared, and then this expression to the power minus 1. But I can also have this relation. So actually what I can do is rewrite this using this relation in terms of E of mu. And actually it's, well, it requires a little bit of manipulations, but not too much, to realize that this is equal to E squared mu 1 minus E squared mu over 12 pi squared times the logarithm of S over mu squared to the power minus 1. So this expression which I have here, lambda can be eliminated from it now. W E plus E minus is going to be expressed purely in terms of the physical coupling constant now. The physical coupling constant which I measured at a particular scale, which is called the renormalization scale mu, then I have my expression in terms of the Mandelstam variables, and then this actually is going to be simply expressed also in terms of E of mu. And so indeed lambda has disappeared. But at the position where I have now, but I previously had lambda, I now have a renormalization group scale which are called mu. And the important difference is that in here I don't want to take mu to infinity. Here I had a cutoff. Lambda was the cutoff which I wanted to take to infinity. But here mu has a different interpretation. It's the same expression, except now that I take mu to be some value of the energy at which I did my first experiment. So mu is not something that has to be sent to infinity. So that's the thing I gained. However, I seem to have lost something else, namely that my expression seems to depend on this arbitrary value of the energy at which I did my experiment. I mean, I chose some particular value mu to do the experiment, and then I write down an expression that seems to depend on this choice of mu. There's one thing you can check, by the way, is that if I take s to be equal to mu squared again, then the logarithm is where I have to put in mu squared, and this logarithm vanishes then, and indeed I get back the result that I got. But this actually should not be dependent. I mean, the left-hand side is some experiment that's not dependent on whatever scale mu I use to do my first measurement. So this is actually going to determine how E depends on mu. E will depend on mu in such a way that this is actually independent. This whole expression is going to be independent of mu. And this is going to give me what's called the renormalization group, in the sense that I can have E of mu at different values of mu, and I just have to tell you how E will depend on mu, and then I'll find that indeed the energy scale determines the value of the electric charge. And the way it goes is by demanding that this expression indeed is independent of mu. So this is how we get eventually what's called the running of the coupling constant. So what's E of mu? Well, I'm going to write down the answer a little implicitly. I'm going to write it in terms of a relation between E of mu and say some other scale, call it mu 0, where I could do my experiment. And this mu 0 could be even a few electron volts. So there is a certain value where we know that alpha, which is E squared over 4 pi, is say 137. And this is, for example, if we take mu 0 to be, say, a few electron volts, something like that. And then E of mu, if the energy increases, is going to be this value, which we know very well. And then we'll find that it starts to depend on energy in the following way. There's this original E mu log mu squared over mu 0 squared to the power minus 1. Sorry. So given E at a value mu 0, then at another value mu, it will look like this. So this is the way things change with energy. And I can actually rewrite this in terms of alpha of mu as in the following way, and this is probably the way in which usually these equations are written. 1 over alpha of mu is 1 over alpha of mu 0 minus, and then what I get in here actually, if I take the factor of 4 pi out, it's 1 over 3 pi logarithm of mu squared over mu 0 squared. This is actually the outcome of the Feynman diagram calculation if I include only the electron. And there's this coefficient here which tells me indeed that I've included the contribution of the electron. But if you indeed include other particles like the muon and so on, this coefficient will change somewhat. But it tells you that this 137, which we know very well and thought of as being a very important fixed number, is not a fixed number at all. If you go to higher energies, its value will change. And for example, at lab energies, there's a considerable change in this outcome. I forgot the precise number, but there's, I think 137 goes like 128, something like that, which is a thing that can be measured and compared to experiment. So this is how loop corrections indeed can be verified to occur in, well, in nature. So in that sense, these well, rather tricky calculations give you physical answers now, which don't depend on any cutoff anymore, and give you an answer that can be verified and compared to experiment. I think I'll conclude here actually. Are there questions about this final outcome? Well, actually, this involves also the fact that I included it in this way in my propagator actually allows me to also include precisely repeated loops like that. So this is actually already included in the diagram, but there are, of course, other more complicated diagrams like with photon lines here or like this, which have not been included. It turns out, however, that this running of the coupling constant is, well, good, very good actually in first order already to be compared to experiment. You can estimate what higher order corrections look like. And actually with supersymmetric theories there is even more cancellations for these higher order corrections. And there people can actually extrapolate their renormalization group flow even much further than simply well, a few orders of energies, but then you can even extrapolate many orders of magnitude, and this is how people indeed calculated that the coupling constants of the various interactions we have, the electric, magnetic, the weak and strong force, eventually converge at a very high energy scale, which I think is about 10 to the 16th GeV. So we're not going to reach that with experiment, but we can trust our calculations up to that order, and it's basically a one-loop calculation that people have done and extrapolated up to that level. Okay. All right. If there are no more questions, then thank you very much for your attention.